This is lab 3 involving black hole analysis. Just for introduction, this lab was meant to simulate and analyze the motion of a star system in orbit around a black hole in order to determine the net force of the star and the mass of the black hole. And CloseScript code was used to create the computer model of the motion. Just the fundamental concepts involved with this lab. We had Newton's second law again, final velocity equals initial velocity plus net force divided by mass times the change in time, which relates net force to the object's motion and is derived from the momentum principle, which we've discussed throughout the semester. And we also use the gravitational force equation, which is this force equals the gravitational constant times mass of object 1 times mass of object 2 divided by the radius squared, which gives you the attractive force between the centers of two objects. And then we also break the net force into its two components, the force acting parallel to the momentum and the force acting perpendicular to the momentum. As we look further into these components, we get them from this momentum principle I just mentioned earlier. And those are the components we've seen for a while where you break momentum down to its parallel and perpendicular. So with the actual code itself, the initial setup I had, my seed was my Georgia Tech email, which gave me a unique set of data. And then here we have the gravitational constant entered in, the star's mass of 2 times 10 to the 30th, and then the delta T involved, which was the amount of seconds in a day, 86,400 seconds. From here, I found initial momentum and final momentum by multiplying the given velocities by the star's mass of 2 times 10 to the 30th to get the expressions for both of those. And then from there, we were able to find delta V and delta P by just subtracting final velocity minus initial velocity, final momentum minus initial momentum. And then we could relate this as dp dt as this change in momentum over change in time. And we know that F net equals dp dt from Newton's second law we've discussed in class. Here were the actual components. First, we found the unit vector p hat, which points parallel to the motion, which is up here, which is initial momentum divided by the magnitude to get this unit vector. And then we can find the parallel component of dp dt by multiplying this p hat times the magnitude. And then we know that the parallel component plus the perpendicular component equals total net force. So we can subtract the parallel component from dp dt to get the perpendicular component, which we have here. So now we have both components. From there, we move into solving for the mass of the black hole, which can be derived from this gravitational force equation from before. As you see here, we have net force times position squared over this gravitational constant times the mass of the star. Then here's where we express the arrows in the orbital motion. We'll see in the next slide. For the scale, I just kind of played around with it. Since the forces are very large compared to our model, it had to be very, very low. As you can see here, I just kind of played around with it until the arrows fit to scale. And then we used the star position for each arrow's position, and then their respective axis is based on which component of the dp dt we're working with. As you can see here, this was at the start or the end of one orbit. The orange arrow is the net force. The light blue one is the perpendicular component, and you can't see it, but the pink arrow was the parallel component, which you can't see because it's so small compared to the others. As you see here, the net force we got was 9.11 times 10 to the 28th. The parallel component was 2.5 times 10 to the 28th, and the perpendicular component was 8.76 times 10 to the 28th. And we got the average. I put all the values for mass into Excel to get the average, which turned out to be 1.31 times 10 to the 34th kilogram for the average mass of the black hole. This kind of interpretation of the results. FNet and dp dt are not the same. They're distinct in how they're calculated, in addition to what they tell us about the given system. FNet is the cause of the momentum change, and dp dt is the effect of this situation. FNet is calculated by summing all the forces of the star, including the gravity equation, and these components are the forces in their respective directions. And the dPdt value was calculated by using change of momentum over the change in time. So it's the speed and direction of the star over the period of the orbits. And then we have a what-if scenario, which what happens if the mass of the black hole changed but the motion position of the star remain the same? Well, this is kind of, you can use the gravitational force equation, and the star's motion would change based on the new gravitational force present, which we could then solve for the new mass of the black hole by plugging into the formula. So we therefore could calculate the new mass in this